Hello guys, Dr. Bans here. Let's talk about the properties of Z transform. Okay, so the first one we shall talk about is called the linearity property. Okay, so here, if x1 of n has a Z transform of x1 of Z, and then it has an ROC of let's say A1 less than mod what Z less than, let's say, B1. Okay, then you have another one, x2 of n also has a Z transform of x2 of what Z, and then it has an ROC of, let's say, A2 less than what, A2 less than mod what Z less than what B2. Okay, then you're going to have A1 into x1 of n plus let's say A2 into x1 of what n. Okay, okay, it's going to be let me make here B2. Okay, let me make here B2. Okay, or let me make here if is A1, let me say here is what B1. Okay, it's going to have a Z what transform. It's also going to have a Z transform of let's say A2. Okay, let's say A2 into x1. Okay, into x1 of what Z plus, let's say, B2 into what B2, or we can, because it's a constant, I think it's better to maintain the constant. So A1, and then it's a constant, so what B1 into what x2. Okay, here, please, here is x1 and here is what x2. Okay, here is x1, so here will be x2 of what of Z. Okay, of Z. Okay, and then so now let me prove this one. So to prove this one, what I can say is that my x of Z, okay, my x of Z is supposed to be actually equals to I just want to adjust it well. Okay, so my x of Z is actually going to be equals to, x of Z is going to be equals to here, summation up to infinity, n is equals to minus what infinity. Okay, x of what n into what Z minus what n, which is going to be equals to summation infinity, n is equals to minus what infinity. Okay, so here A1 x1 of what n plus what B1 x2 of what n. Okay, into Z exponent minus what n. Okay, so here I can say that summation up to infinity, n is equals to minus infinity. Okay, A1 x1 of what n into Z minus n. Okay, plus here like this, n is equals to minus infinity. Okay, so here let's say I can have B1. Okay, I can have B1 x2 of what n. Okay, into Z minus what n. Okay, so now when I have this one, obviously this place is supposed to give me what A1 is supposed to give me, obviously give me A1, okay, x1 of what Z. Okay, plus what B1 x2 of what Z. Okay, so now what I can say is that A1 x1 of n, okay, plus B1 x2 of n is going to have a transform, a Z transform of A1 x1 of what Z plus plus B1 Z2 of what Z. So it's proven. Okay, let's go to the second one. So now in the second one, I'm going to have number 2. Okay, number 2 is called time shifting property. Okay, time shifting property. So in time shifting property, okay, if x of n has a z transform of x of what? Z. Okay, and the ROC here is A1, sorry, is A less than what? Z less than what? B. Okay, then you're going to have n minus what? K. Then you're going to have n minus k also having a z what? Transform. A z transform of what? X of what? Z into z minus what? K. Okay, you're going to have this. Okay, so now if how do I prove this one? So to prove this one, what I can say is that x of what? Z. Okay, what I can say, n is equals to minus what? Infinity. Okay, so here x of n minus what? K into z minus n is equals to what? Is going to be equals to here. What I can say is that to have this one, let me say that let n minus k to be equals to what? M. Okay, and then let n to be equals to m plus, okay, and let n to be equals to m plus what? K. Okay, so now if I have that one, then my x of what? Z is now going to be here infinity, n is equals to minus what? Infinity, x of what? M into what? Z into minus what? Minus m plus what? K, which is going to give me summation up to what? Infinity, n is equals to minus what? Infinity, x of what? M into what? Z minus what? M into z minus what? K. Okay, so if I do that, then what I can say is that this one will give me what? 1 transform, which is equals to what? X of what? Z. Okay, and then this one will remain z of minus what? K. So now I can say that if I have x of n minus what? K, and I pass it through a z transform, I'm supposed to get x of what? Z into z minus what? K. Right? Into z minus k. Okay, so that is what I will get over there. So now you can see that this is what? Proving. Okay, because it's the same thing over here that we set out to what? Work out for. Okay, so it's proving. Now let's go to the next one that we need. Okay, property number 3. So let's go on to property number 3. So property number 3, that is what? Scaling in Z domain. So let's look at the scaling in Z domain. If x of n, okay, has a Z transform, okay, of x of what? Z, okay, and then it has an ROC, okay, of what? A1 less than, okay, Z, and then less than what? B1, okay. Then here what you're going to get is that if we have a exponent n x of what? N, okay, then it will also have a Z transform of what? X of what? Z on what? A, okay, and the ROC here is going to be A less than mod Z over A, okay, less than mod Z over what? A, okay, less than what? B. Alright, okay, so let's say here is B1, here is what? A1. Okay, so basically this is what we have. Let's prove this theorem. Okay, so to prove this theorem, x of what? Z is equals to what? A exponent n is equals to what? Z transform, okay, of A exponent n into x of what? N, okay, into x of n, which is equals to here summation up to infinity, n is equals to minus what? infinity. Okay, you have a exponent n into x of what? N into what? Z minus what? N. Okay, this is what you have here. Okay, so now if you have this one over here, then what we can do from here is that we can just see what we can do about it. So to move this particular proving forward, what I have to let you know is that you know that if you have something like here, z exponent minus n is also equals to 1 over what? Z 1 over 1 over n exponent what? 1 over z exponent what? N, like this. You know that you have this one. Okay, this is correct. All right. Okay. Then also, if you have something like a exponent n, is also equals to 1 over a exponent minus what? Exponent minus what? N. Okay. So now, having that assumption in mind, then this place, I can rewrite it. Okay. I can now rewrite my x of z to be equals to here infinity, n is equals to minus what? Infinity. Okay. And then I can write it at x of what? N here. Okay, and here I'll write it at what? Z over what? A. Z over A into what? Exponent minus what? N. Okay, I can rewrite it at this way. Okay, so now if I rewrite this one as this way, then you know that this one and this one, it constitutes what? One Z transform. So I'm just going to have a Z transform of what? Z over A. Okay, so in the nutshell, I'm going to have a Z transform such that A, N, okay, into x of what? N should give me a z transform. Should give me a z transform of what? Of x z over what? A, which is correct as compared to what I set out to what? Get here. Okay, so this is what? Correct. All right. Now let's go to our next property, which is property number 4. So now property number 4 is called time reversal, okay, property. Okay, so how do we deal with the time reversal property? Okay, so if x of what? N has a z transform of z of what? Of x of z, and then the ROC here is such that A is less than mod z is less than B. Okay, then I'm going to have here x of minus n, okay, is going to be what? Zt into what? X of z minus what? 1. Okay, so here, and then my ROC is going to be what? A less than z inverse less than what? B. Okay, so here I'm set out to prove this particular theorem also. Okay, set out to prove this particular theorem. Okay, so to prove this one, what I can say is that x of z is equals to what? Summation infinity, n is equals to minus infinity. Okay, here I can have x of minus what? N into what? Z of minus what? N. Okay, so this is what I can have. Okay, so now if I have this one, I can say that let n is to be equals to what? Minus n. Okay, let n to be equals to minus n. If I do that, then x of what? Z is going to be equals to what? Summation. Let me leave my limit right now. Here is going to be what? X of what? N. Okay, and then here is going to be what? Here also it is actually going to change here because n is equals to what? Minus n. So here will be what? N. So now because I have changed these ones, my limit will now change from this place, from this one to what? Here it will become positive infinity down here, and here and here it will become what? Negative what? Infinity. Okay, now to move this particular this thing forward, I can say that summation. Okay, let me leave my limit right now and come later. Okay, here I can write this one in this way. Okay, z minus what? 1 into what? Minus what? N. Okay, and then you see, if I interchange the summation, my answer will not what? Change. Okay, so I can continue to say that here is minus infinity, and here is what? Infinity. Changing the summation this way, changing the limit in this way doesn't change my what? My answer in any way. Okay, so now if you see that this one and here is one what? Transform. So now my transform is going to be what? X of minus what? N is now going to have what? A Z transform of what? X here and here is one what? Transform. This one and this one is a transform. Okay, so I'm going to have X of what? Z minus what? 1. So this is going to be my transform. Okay, so you can see that it is what? Proven. Alright, now let's go to the next transform. Okay, so let's continue from property. We are now on property number 5. So that is differentiation. Differentiation in Z domain. Okay, in Z domain. Okay, so here, if you have X of what? N, that gives you a Z transform of X of what? Z. And you have an ROC of what? Of, let's say, A1, A, okay, less than Z, okay, less than mod Z, less than what? B, okay, then you're gonna have NX of N, okay, also having a Z transform of the differentiation here, minus Z, D on what? DZ, okay, X of what? Z. And this will also have an ROC, okay, whereby it doesn't change. A is less than mod Z is less than what? B. Okay, so now let's prove this one. Okay, so to prove this one, you state the general Z transform formula, which is what? X of what? Z is equals to what? S of Z is equal to summation up to infinity, N is equals to minus what? Minus infinity. X of what? N into Z minus what? N. Okay, so you just take this general Z transform what? Formula. General Z transform formula. So now, with this formula, then what you can do is you can just differentiate both sides. Okay, you can just differentiate both sides. So to differentiate both sides, what you can say is that D on what? DZ, okay, into X of what? Z is equals to what? Is equals to summation up to infinity, N is equals to minus what? Infinity, okay, X of what? N. Then you differentiate this side, okay, differentiate this side. Alright, so you differentiate this side. To differentiate this side, you know that it's minus N, okay, minus N, okay, into, if you differentiate into what? Minus N minus 1, alright, and the minus N will come here, alright, yeah, so that is how the differentiation will actually be alike. Or, okay, or I can say that D of what? Z minus what? N over what? DZ, because I differentiated this here with respect to what? DZ. Okay, so now if I do that, I'm going to have D of what? Here, D of what? X of what? Z over what? DZ is actually equals to what? It's actually equals to here is actually equals to summation, okay, N is equals to minus what? Infinity, X of what? N, okay, and then here if I differentiate this one, I'm going to actually get minus N, okay, minus N into what? Into Z, okay, minus N minus 1, okay, so this is what I'm going to get over here, alright, so this is what I'm going to get over here. Okay, so now when I get this one, then what I can do is, okay, so this one, what does this mean? Okay, so D of what? X of what? Z over what? DZ is equals to what? Here, what am I going to get here? Okay, okay, so what I'm going to get here is, I'm going to get here summation up to infinity, N is equals to minus infinity, okay, X of what? N into what? Minus what? N, Z minus what? N. This one, okay, is I can bring it what down here to be what z. All right, so that's what I can do there. So moving this forward, then I can say that this place I can say that is actually equals to summation up to what infinity, n is equals to minus what infinity. I can bring n here, okay. I can bring n here, and I can bring x of what n here, all right, and then I can have what z exponent minus n here, okay. Then I can have what over minus what z here. Okay, so when I have this one here, then what I can say is that minus what z over what d on the what dz on dz into x of what z is actually equals to what summation of what summation of infinity, n is equals to minus what infinity. Okay, here x of what n into z minus what n. All right, so I can actually say that. I can actually say that. All right. Okay. So now, if I have that, then basically my this thing is what already proven. Okay, because you can see that whatever I set out to achieve, I have here. Sorry, this n, this n. Okay, this n must represent here. This n, it must come here. Okay, so now you can see that this one that I set out to achieve, okay, is already here, okay, and then this one, okay, is also what here, okay. So now you can see that this from except for this n, all the terms here is for what x of what z is for x of z is the Fourier transform, because this formula is the formula for Fourier transform, which gives what x of z, except for this n. Okay, and we know that x of z is also gives what x of n. Okay, so I can now say that I can now confidently say that minus z over d on d over d. Okay, sorry, let me rewrite it. Okay, I can now say that minus z on d on what dz. Okay, x of what z. Okay, is equals to what? Is equals to n x of what n. Okay, as I set out to prove over here. Okay, so now it's actually proven here because what you can now see is that this one, okay, apart from this n, this one is a transform that gives x of z. You know that x of z vice versa gives what x of n. So instead of x of z, I can write of x of n, and this n is what over here. So it's proving here as I set out to achieve. Okay, as I set out to achieve from here. Okay, so now it's proving. Here. Okay, so now let's go on to the next one. So let's prove the conjugate. Okay, let's prove the conjugate. Okay, so let's prove the property number 6. Okay, conjugation of a complex sequence. Okay, conjugation of a complex sequence. Okay, let's prove the conjugation of a complex sequence. Okay, so now here, if x of n has a transform of x of what z, okay, and the ROC is what a less than mod z less than b, then x conjugate, okay, x conjugate, okay, the complex conjugate of x, okay, of n will also have a z transform of x conjugate, okay, into what z what conjugate. Okay, so the ROC here is ROC here is going to be same, A less than mod Z less than what B. Okay, so this is what we're going to have. Alright, then if we have this one, so let's quickly prove it. Okay, so now Z of what? X of what? N is going to be equals to summation up to infinity, n is equals to minus infinity. So now here x of here, and then here of what? N is going to be what? Z. Okay, minus what? N. Okay, so this is what we're going to have. Okay, so now if we have this is equals to summation, okay, is going to be equals to here x of what? N. Okay, into, if I take this conjugate outside, okay, if I take it outside, okay, if I take it outside, then here is going to be conjugate here, okay, and then it's going to be here like this minus what? N. In that case, my conjugate, in that case, the conjugate on this x will come outside. The complex conjugate on this s will come outside. Okay, so now if I have this, you see that now it's proving. Okay, so if I have this, then now I can say that x star of what? N has a z transform of what? Of here. Okay, see that this guy is outside. You see that this, the whole formula is what? Is that for what? For obtaining the z transform, except for what? This conjugate. So now what it means is that if I get my z transform, there will be a conjugate here and there will be a conjugate here. Okay, so now the proving is already done. So if I get my dot, so now this conjugate will come here. Okay, and then this z also, the z also will have its own conjugate coming here. This one, it will come here like this, and then I'll get my minus what? In. Alright, so basically this is how you can prove this one. Very simple and easy, the conjugate approach. Okay, so now let us see another one. Okay, another one. Okay, so let's see property number 7, which is convolution property. Convolution. Okay, convolution property. Okay, the convolution property. Convolution property, that is a very easy one. Property number 7. Okay, that is property number 7. Okay, so how do we deal with the convolution property? Okay, so now here, if x1 of n has a z transport of x1 of what? Z. Okay, and then you have x2 of n also having a z transform, okay, of what? X2 of what? Z. Okay, then what are you going to expect here? Your ROC is what? Okay, so here your ROC is A1 less than what? Mod Z less than what? B1. Okay, here your ROC is what? A2 less than mod Z less than what? B2. Okay, so now here, then you're going to have in terms of your convolution, x1 of n convoluting with what? x2 of what? N. Okay, to give what? To give zt. Okay, to give zt. Okay, which is going to be x1 of z into what? x2 of z. Okay, x2 of z. Okay, so now your ROC in this case will be intersection of what? x1 of z, okay, and what? x2 of what? Z. Okay, all right. So now let's see how we can prove this one. To prove this one, first we must define what? Convolution. Okay, so we know that when we mention convolution, it is actually equals to, let's say we have x1 of n convoluting with what? x2 of what? N. Okay, then we're supposed to have what? Let's say k is equals to minus infinity. Here is what? Infinity. Okay, we're going to have what? x1 of n, okay, into what? x2 of what? N minus k. Okay, so basically this is the definition for what? Convolution. You must always know this one. Okay, convolution is very important in signals and systems. You must always know the definition. So this is the definition for convolution. Okay, so now if we have this one, then what it means is that we're going to find the Z transform for this one. Okay, so now x of what? X of Z, okay, is going to be equals to what? Here like this, k is equals to minus, k is equals to what? N is equals to what? Infinity. Okay, so and then you're going to find for this one. So now I'll put this one into the equation. That is, here k is equals to minus what? Infinity. Here is what? Infinity. Okay, so I'm going to have x1 of n into x2 n minus what? K. Okay, into okay, so this is what I'm going to actually what? Have. Okay, so now I will close it into what? Into z minus what? N. Okay, so I put this one into the Z transform general what? Equation. Okay, so basically this one is equals to what? It's equals to here, the infinity, and it's equals to minus what? Infinity, x of what? N into Z minus what? N. And my x of n is what? Is my convolution. Okay, so this place is actually equals to what? My convolution, which is what? X of what? N. Alright, so basically that is how you can do this one. Then you go on then continue with the proving. Okay, so now when you have done it this way, then what you can now say is that your x of what? Z, okay, is now equals to if I should bring this one, x1 of okay, wait a minute, please. This place is k, x1 of k, sorry, x1 of what? K. So x1 of what? K. Alright, if I don't do it that, I'll make a mistake. Okay, x1 of k. Okay, so now I can bring my summation up to what? Infinity. Okay, and k is equals to what? Minus what? Infinity. See that it matches with this x1 of k. So now I'll make here x1 of what? K. See that k is equals to minus infinity, and here is also what? K. Okay, then the next summation, should I have two summations here? So the first one I have given it to this guy. This second one I'll take it to the x2. Okay, so now here infinity, n is equals to minus what? Infinity. And then I'll make here what? X2 what? N minus what? K into what? X minus what? N. Okay, but what you can deduce from here is that whenever you have here like this, n is equals to minus what? Infinity. Okay, and then you have here x2 n minus what? K, n minus k into z minus n. Okay, you see that it is the same thing as what? Our time shifting. So please, you can revisit the time shifting property that we did. That what we have here is the same thing as what? Time shifting. And what did we get for time shifting? When we had something like this, okay, what we got was that it was what? X of what? K into what? It was what? X of what? Z. You can revisit your time shifting. It was X of Z into what? Into Z minus what? K. Okay, into Z minus K. Okay, so this is what we got here. So now instead of, so here, see that is x2. So I'll put 2, or I also put 2 here. Okay, I also put 2 here. So now I can put this one into my equation, and my x of z will now be equals to here, summation, okay, k is equals to minus what? Infinity. Here is infinity. X1 of what? K. And then here, what am I going to get here? You see that here is going to be what? Is going to, instead of writing this one, I'll put this one there. It's going to be what? X2 of what? Z into what? Z minus what? K. Okay, so now I can take Z2 of X2 of Z outside the summation. Okay, so now X2 of Z, because it's not being affected, because here is K. Okay, but see that here there's no K here. So it's quite different from the summation I have here. Here is K, here is K, here is K. But this guy, X2 of Z, is quite different. So I can take him outside. He's behaving like a constant. So X2 of what? Z into summation what? Infinity. K is equals to minus what? Infinity. Okay, so now if you have this one, then what you're going to get is, now you can bring your what? X1 of what? K. You can bring your X1 of K, and then your Z of what? Minus what? K. Okay, you see that this one is also another what? Z transform. So now your X of what? Your X of Z is now equals to what? X2 of what? Z. And here is also another what? Z transform, which is what? X1. X1 of what? Of what? Z. So now you see that it is what? Proving. It is proving. Okay. So these are some of the problems that you have to prove. See you in the next class.